Have you ever stood at the base of a huge dam and just wondered, how in the world does that wall of concrete hold back an entire lake? Well, it all comes down to mastering an invisible but incredibly powerful force. Okay, let's get into it.
So yeah, this is our big question. I mean, it seems almost impossible, right? The sheer crushing weight of all that water just pushing day in and day out. But engineers have totally cracked this code. And the secret isn't just about making the wall thicker. The answer is all about understanding and calculating this invisible force. It's a pressure that isn't the same everywhere. It's a power that just builds and builds the deeper you go. And that is exactly what we're going to break down today.
All right, first things first. To really get a handle on this, we need to talk about the basic concept at play here. The pressure that any fluid, in this case water, exerts when it's just sitting still. This right here is the key. It's called hydrostatic pressure. Now, don't let the formula scare you. It's pretty simple. P is the pressure we're trying to find. Then you have rho, that Greek letter rho, which is just the density of the fluid. G is for gravity, of course, and the real star of the show today is H, the depth. So, imagine you're just dipping your hand into a swimming pool. Right there at the surface, that H in our formula is basically 0, so the pressure is super low. You can't even feel it, right? That's because there's hardly any water sitting on top of your hand. Simple enough. But this is where water really shows its muscle. As you go deeper, that H value starts to shoot up. For every single foot you go down, you're adding the weight of a whole column of water on top of you, and the pressure just skyrockets. This direct link between depth and pressure, that's the first huge piece of the engineering puzzle. So, we know pressure gets stronger the deeper you go. But for an engineer designing a dam or a submarine, knowing the pressure at one tiny point isn't enough. They need to figure out the total push over the entire surface. And that brings us to the total pressure force. Think of it as adding up all those little pressures across the whole area. And notice that little detail on the slide. The force is always normal or perpendicular to the surface. That's so important because it tells engineers the exact direction of the push they need to fight against. Okay, now here's where the math gets really clever. Check out this formula. It looks familiar, right? But we've added A for the total area of the surface. And then there's that H prime, which stands for the depth to the object's geometric center, its center of gravity, its physical balancing point. And this right here is what makes it so brilliant. You don't have to calculate the pressure at a million different points. All you do is find the pressure at the geometric middle of the object, then multiply that by its total area, and boom, you've got the total force. It's an amazing shortcut. All right, so now we know how much force is pushing on our wall. That's huge. But believe it or not, that's only half the battle. The next question is maybe even more important for stopping a total disaster. So where is that one single point where all that force is being applied? Is it right there in the middle at the center of gravity we just used? Or is it somewhere else? This, folks, is the literal and figurative tipping point. And this leads us to two really different concepts. You've got the center of gravity, that's just the geometric middle of an object's shape, but then you have the center of pressure. That's where the total force of the water actually acts. One is a property of the object, the other is a property of the force. They are not the same thing. And here is the big secret, the thing every engineer has to know. For any vertical wall, any dam face, the center of pressure, that point where all that force hits, is always lower than the geometric middle. This is a non-negotiable rule of physics. So why? Why is it always lower? Well, remember, the pressure isn't uniform. It's weak at the top and incredibly strong at the bottom. This makes the force distribution totally bottom-heavy. Because there's so much more force pushing on the lower half, the average point of all that force gets dragged downwards, and that's why you have to reinforce the wall there, not in the middle. So, now that we've got the physics down, let's put it all together. Let's see how engineers take these ideas and build things that can laugh in the face of these incredible forces. It really comes down to this four-step playbook. First, you define your surface. Step 2, you calculate the total force pushing on it using our formula. Step 3, and this is the crucial one, you find that center of pressure. That tells you where the force is hitting. And finally, step 4, you reinforce the heck out of that spot. And this stuff doesn't just work for flat walls. What if the surface is sloped? Same principles, you just have to account for the angle. What if it's curved, like a big dam? Engineers have a slick trick for that. They just break the force down into two parts: a simple horizontal push, which we know how to deal with, and a vertical push, which is just the weight of the water sitting right on top of the curve. It's such an elegant solution. Now, once you really start applying these principles, you stumble into some truly weird, mind-bending results. And one of the most famous is something called the hydrostatic paradox. It's going to mess with your intuition a little bit. Check this out. In this example, the actual weight of the water in the tank is around 70,000 newtons, but the force pushing down on the bottom of that tank is over 280,000 newtons. That's 4 times the actual weight of the water inside. It doesn't seem to make sense, but because pressure acts in all directions, it's absolutely real. It's a paradox that keeps engineers on our toes. I mean, it really makes you think, doesn't it? Just by understanding how water behaves when it's sitting still, we've built these incredible structures that hold back oceans. It kind of leaves you with one last big question. What other invisible, powerful forces are out there all around us, just waiting for us to figure them out?